Hello everyone, this is Saurabh from Edureka, and today we'll be discussing about convolutional neural networks. So without any further ado, let us move forward and have a look at the agenda for today. So we'll begin by understanding how a computer reads an image. Then we'll see why can't we use fully connected networks for image recognition. After that, we'll understand what exactly is convolutional neural network and how it works. And finally, we'll be looking at a use case. So let's begin, guys. We'll understand how exactly a computer reads an image. So this is an image of New York skyline. I personally love this picture. So when a human will see this image, he'll first notice there are a lot of buildings in different colors and stuff like that. But how a computer will read this image? So basically there will be three channels. One will be red, another will be green, and finally we have blue channel, which is popularly known as RGB. So each of these channels will they have their own respective pixel values, as you can see it over here. So when I say that image size is B cross A cross 3, it means that there are B rows, A columns, and 3 channels. Alright, so if somebody tells you that the size of an image is 28 cross 3 pixels, it means that it has 28 rows, 28 columns, and 3 channels. So this is how a computer sees an image. And this is for colored images. For black and white images, we have only 2 channels. So let's move forward and we'll see why can't we use fully connected networks for image classification. So consider an image which has 28 cross 3 pixels. So when I feed in this image to a fully connected network like this, then the total number of weights required in the first hidden layer will be 2352. You can just go ahead and multiply it yourself. All right. But in real life, the images are not that small. All right. So whatever images that we have, they are definitely above 200 cross 3 pixels. So if I take an image which has 200 cross 3 pixels and I feed it to a fully connected network, so at that time, the number of weights required at the first hidden layer itself will be 120,000, guys. So we need to deal with such huge amount of parameters, and obviously we require more number of neurons. So that can eventually lead to overfitting. So that's why we cannot use fully connected network for image classification. Now let's see why we need convolutional neural networks. So basically, in convolutional neural network, a neuron in the layer will only be connected to a small region of the layer before it. So if you consider this particular neuron which I'm highlighting right now is only connected to 3 other neurons. Unlike the fully connected network where this particular neuron will be connected to all these 5 neurons. Because of this, we need to handle less amount of weights, and in turn, we need less number of neurons as well. So let us understand what exactly is convolutional neural network. So convolutional neural networks are special type of feed-forward artificial neural networks, which is inspired from visual cortex. So visual cortex is nothing but a small region in our brain which is present somewhere here where you can see the bulb. And basically what happened, there was an experiment conducted and people got to know that visual cortex is small regions of cells that are sensitive to specific regions of visual field. So what I mean by that is, for example, some neurons in the visual cortex fires when exposed to vertical edges. Some will fire when exposed to horizontal edges. Some will fire when exposed to diagonal edges. And that is nothing but the motivation behind convolutional neural network. So now let us understand how exactly a convolutional neural network works. So generally a convolutional neural network has 3 layers: convolution layer, ReLU layer, pooling layer, and fully connected layer. We'll understand each of these layers one by one. We'll take an example of a classifier that can classify an image of an X as well as an O. So with this example, we'll be understanding all these 4 layers. So let's begin, guys. Now there are certain trickier cases. So what I mean by that is X can be represented in these 4 forms as well, right? So these are nothing but the deformed images of X. Similarly for O as well. So these are deformed images. So even I want to classify these images either X or O. All right, because even this is X, this is X, this is X, this is X. But all these are deformed images, but they are in turn X, right? So I want my classifier to classify them as X. So basically that's what I want. So if you can notice here, this is a proper image of an X, and which is actually equal to this particular X, which is a deformed image. Same goes for this O as well. So now what we are going to do is, we know that a computer understands an image using numbers at each pixels. So what we'll do, whatever the white pixels that we have, we are going to assign a value -1 to it, and whatever black pixels we have, we are going to assign a value 1 to it. When we use normal techniques to compare these two images, one is a proper image of X and another is a deformed image of X, we got to know that a computer is not able to classify the deformed image of X correctly. Why? Because it is comparing it with the proper image of X, right? So when you go ahead and add the pixel values of both of these images, you get something like this. So basically our computer is not able to recognize whether it is an X or not. Now what we do with the help of CNN, we take small patches of our image. So these patches or these pieces are known as nothing but features or filters. So what we do, by finding rough feature matches in roughly the same positions in two images, CNN gets a lot better at seeing the similarity between the whole image matching schemes. What I mean by that is, we have these filters, right? We have these filters that you can see. So consider this first filter. This is exactly equal to the feature or the part of the image in the deformed image as well. So this is our proper image and this is our deformed image, alright? So this particular feature or this particular part of the image is actually equal to this particular part of the image. Same goes for this particular feature or filter as well. And similarly, we have this filter as well, which is actually equal to this particular part of the deformed image, alright? So let's move forward and we'll see what all features that we'll be taking in our example. So we'll be considering these three features or filters. This is a diagonal filter, this is again a diagonal filter, and this is nothing but a small x. So we'll take these three filters and we'll move forward. So what we are going to do is we are going to compare these features, the small pieces of the bigger image. We are going to put it on the input image, and if it matches, then the image will be classified correctly. Now we'll begin, guys. The first layer is convolution layer. So these are the beginning two steps of this particular layer. First, we need to line up the feature in the image and then multiply image by the corresponding feature pixel. Now let me explain you with an example. So this is our first diagonal feature that we'll take. We are going to put this particular feature on our image of x, all right? And we are going to multiply the corresponding pixel value. So 1 will be multiplied with 1, we'll get 1, and we'll put it in another matrix. Similarly, we are going to move forward and we're going to multiply -1 with -1. We're going to multiply -1 with -1, as you can see. Similarly, we multiply this as well, -1 into -1, then again -1 into -1. So we are going to complete this whole process when we are going to finish up this matrix. All right. And once we are done finishing up the multiplication of all the corresponding pixels in the feature as well as in the image, we need to follow two more steps. We need to add them up and divide by the total number of the pixels in the feature. So what I mean by that is, after the multiplication of the corresponding pixel values, what we do, we add all these values, we divide it by the total number of pixels, and we get some value, right? And then now our next step is to create a map and put the value of the filter at that particular place. We saw that after multiplying the pixel value of a feature with the corresponding pixel value of with that of our image, we get the output, which is 1. So we place 1 here. Similarly, we are going to move this filter throughout the image. Next up, we are going to move this filter here. After that, we are going to move it here, 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 everywhere on the image. We are going to move it and we are going to follow the same process. All right, so yeah, this is one more example where I've moved my filter in between, and after doing that, I've got the output something like this, 1, 1, -1 and all. So over here, if you notice, I've got couple of times -1 as well, due to which my output that comes is 0.55, right? So I'm going to place 0.55 here. Similarly, after moving the pixel, after moving the filter throughout the image, I got this particular matrix. All right, and this is for one particular feature. After performing the same process for the other two filters as well, I've got these two values. So we have these three values after passing through the convolution layer. Let me give you a quick recap of what happens in convolution layer. So basically we have taken three features, all right, and one by one we'll take one feature, move it through the entire image, and when we are moving it, at that time we are multiplying the pixel value of the image with that of the corresponding pixel value of the filter, adding them up, dividing by the total number of pixels to get the output. So when we do that for all the filters, we got these three outputs, all right? So let's move forward and we'll see what happens in ReLU layer. So this is ReLU layer, guys, and people who have gone through the previous tutorial actually know what it is. So let me just give you a quick introduction of ReLU layer. So ReLU is nothing but an activation function. All right. So what I mean by that is it will only activate a node if the input is above a certain quantity. While the input is below 0, the output is also 0. All right. And when the input rises above the certain threshold, it has a linear relationship with the dependent variable. Now I'll explain you with an example. We have a graph of ReLU function here. So my function says that when f of x is equal to 0 if x is less than 0, and it is equal to x when x is greater than 0. All right. So whatever values that I have which are below 0 will actually in turn become 0, and whatever values that are above 0, our function value will also be equal to that particular value. So f of x will be equal to x if it is greater than or equal to 0, and it will be 0 if it is less than 0. So if I have x value as -3, so definitely it is less than 0, so f of x becomes 0. Similarly, if I have -5x value, then again it is less than 0, so my f of x value becomes 0. But when I consider 3 as my x value, then my f of x becomes equal to x, which is nothing but 3. So over here I'll have 3. Again, if I take my x value as 5, then obviously it is greater than or equal to 0. Then my f of x becomes equal to x, so my f of x value becomes 5. So this is how a ReLU function works. So why are we using ReLU function here is we want to remove all the negative values from our output that we got through the convolution layer. So we'll only take the first output that we got by moving one feature throughout the image. So this is the output that we have got for only one filter. All right. So over here, I'm going to remove all negative values. So over here, you can see that it was -0.11 before, and I've converted that to 0. Similarly, I'm going to repeat the whole process for the entire matrix. And once I'm done with that, I get this particular value. Now remember, this is only for the output that we got through one feature. Alright, so when we were doing convolution at that time, we were using 3 features, right? So this is the output only for one filter. After doing it for the output of the other 2 filters as well, we have got these 2 values more. So totally we have these 3 values after passing through ReLU activation function. Next up, we'll see what exactly is pooling layer. So in pooling layer, what we do, we take a window size of 2 and we move it across the entire matrix that we have got after passing through ReLU layer. And we take only the maximum value from there so that we can shrink the image. So what we are actually doing is we are reducing the size of our image. So let me explain you with an example. So this is basically one output that we have got after passing through ReLU layer. And over here we have taken a window size of 2 cross 2. So when we keep this window at this particular position, we see that 1 is the highest value. So we are going to keep 1 here. And we are going to repeat the same process for this particular window as well. So over here the maximum value is 0.33, so 0.33 will come. So if you notice here, earlier we had 7 cross 7 matrix and now we have reduced that to 4 cross 4 matrix. So after doing that for the entire image, we have got this as our output. This output we have got after moving our window throughout the image that we have got after passing through ReLU layer, right? And when we repeat this process for all the 3 outputs that we have got after the ReLU layer, then we get this particular output after pooling layer, right? So basically we have shrinked our image to a 4 cross 4 matrix. Now comes the tricky part. So what we are going to do now is stack up all these layers. So we have discussed convolution layer, ReLU layer and pooling layer. So I'll just give you a brief recap of what all things we have discussed. In convolution layer, what we did, we took 3 features and then after that one by one we moved each filter throughout the image. And when we were moving it, we are continuously multiplying the image pixel value with that of the corresponding filter pixel value. And then we were dividing it by the total number of pixels. All right. With that, we got 3 output after passing through the convolution layer. Then those 3 output we passed through a ReLU layer where we have removed the negative value. All right. And after removing negative value, again, we have got the 3 outputs. Then those 3 outputs we passed through pooling layer. So basically we're trying to shrink our image. And what we did, we took a window size of 2 cross 2, moved it through all the 3 outputs that we have got through ReLU layer. And after doing that, we were only taking the maximum value, pixel value in that particular window. And then we were putting it in a different matrix so that we get a shrinked image. And after passing it through pooling layer, we have got a 4 cross 4 matrix. And since we took 3 features in the beginning, so therefore we have got 3 outputs after passing through pooling layer. All right. Next up, we are going to stack up all the layers. All right. So let's do that. So after passing through convolution, ReLU and pooling, we have got this 4 cross 4 matrix. This was our input image. Now when we add one more layer of convolution, ReLU and pooling, we have shrinked our image from 4 cross 4 to 2 cross 2 as you can notice here. Now we are going to use fully connected layer. Now what happens in fully connected layer? The actual classification happens here guys, okay? So what we are doing here is we are going to take the shrinked images and put it into a single list. So basically this is what we have got after passing through 2 layers of convolution, ReLU and pooling. And this is what we have got. So basically we are converting into a single list or a vector. How we do that? We take the first value 1, then we take 0.55, then we take 0.55, then we take 1 again. Then we take 1, then we take 0.55, 0.55, 0.55. Then we again take 0.55, 1, 1 and 0.55. So this is nothing but a vector, or you can say a list. If you notice here that there are certain values in my list which are high for X. And similarly, if I repeat the entire process that we have discussed for O, there will be certain different values which will be high. So for X, we have first, fourth, 5th, 10th and 11th element vector values are high. For O we have 2nd, 3rd, 9th and 12th element vector which are high. So basically we know now if we have an input image which has 1st, 4th, 5th, 10th and 11th element vector values high, we know that we can classify it as X. Similarly, if our input image has a list which has the 2nd, 3rd, 9th and 12th element vector values high, then we can classify it as 0. Now let me explain you with an example. So after the training is done, after doing the entire process for both X and O, you know that our model is trained now. Okay, so we have given a new input image and that input image passes through all the layers, and once it has passed through all the layers, we have got this 12 element vector. Now it has 0.9, 0.65, all these values, right? Now how do we classify it, whether it is an X or O? So what we do, we'll compare this with a list of X and O. Right, so we have got the list in the previous slide. If you notice, we have got 2 different lists for X and O. We are going to compare this new input image list that we have got with that of X and O. Right, so first let us compare that with X. Now, as I've told you earlier as well, for X, there are certain values which will be high, which is nothing but 1st, 4th, 5th, 10th and 11th value, right? So I'm going to sum first, fourth, fifth, 10th and 11th value, and I've got 5. 1 plus 1 plus 1 plus 1 and plus 1. So 5 times 1, I've got 5. And now I'm going to sum the corresponding values of my input image vector as well. So the first value is 0.9, then the fourth value is 0.87, fifth value is 0.96, 10th value is 0.89, and the 11th value is 0.94. So after this, doing the sum of these values, I've got 4.56. When I divide this by 5, I got 0.91, right? Now this is for X. Now when I do the same process for O, so in O, if you notice, I have second, third, ninth and 12th element vector values as high. So when I sum these values, I get 4. And when I do the sum of the corresponding values in my input image, I've got 2.07. When I divide that by 4, I got 0.51. And so now we notice that 0.91 is a higher value compared to 0.51. So when we have compared our input image with the values of X, we got a higher value than the value that we have got after comparing the input image with the values of O. So the input image is classified as X. Alright, so now let us move towards our use case. So this is our use case, guys. So over here, what we are going to do is we are going to train our model on different types of dogs and cat images. And once the training is done, we are going to provide it an input and it will classify whether the input is of a dog or a cat. Now, let me tell you the steps involved in it. So what we are going to do in the beginning is obviously first we need to download the data set. After that, we are going to write a function to encode the labels. Labels are nothing but the dependent variable that we are trying to predict. So in our training data and testing data, obviously we know the labels, right? So on that basis only we can train our model. So we are going to encode those labels. After that, we'll resize the image to 50 cross 50 pixel and we are going to read it as a grayscale image. Then we are going to split the data, 24,000 images for training and 50 for testing. Once this is done, we are going to reshape the data appropriately for TensorFlow. Now TensorFlow, I think everyone knows about TensorFlow. TensorFlow is nothing but a Python library for implementing deep learning models. Then we are going to build the model, calculate the loss. It is nothing but categorical cross entropy. Then we are going to reduce the loss by using Adam optimizer with a learning rate set to 0.001. Then we are going to train the deep neural network for 10 epochs. And finally, we are going to make predictions. All right, so I'll just quickly open my PyCharm and I'll show you the code, how it looks like. So this is the code that I've written in order to implement the use case. In the beginning, I need to import the libraries that I require. And once it is done, what I'm doing, I'm defining my training data and the testing data. So train and test one contains both my training data as well as testing data respectively. Then I've taken my image size as 50 and learning rate I've defined here. And I've given a name to my model. You can give whatever name you want. All right, so first thing that we saw, we need to encode the dependent variable. That's what we are doing here. We are encoding our dependent variable. So whenever the label is cat, then it will be converted to an array of 1, 0, and when it is dog, it will be converted to an array of 0, 1. So why we are actually encoding the label? Because our code cannot understand the categorical variable. So we need to encode it, right? Next, what I'm doing is I'm resizing my image to 50 cross 50 and I am converting it to a grayscale image, right? And once this is done, I'm going to split my data set into training and testing parts. So yeah, we are basically splitting the data set into two parts for training and testing. And here we are defining a model. So you can I can just go ahead and throw in a comment here. Building the model. Yeah. So this is where we are building the model. So basically what we have done here is we have resized our image to 50 cross 50 cross 1 matrix, and that is the size of the input that we are using, right? This input that I'm talking about. Then what we have done, a convolution layer we have defined with 32 filters and a stride of 5 with an activation function, a ReLU. And after that we have added a pooling layer, max pool layer. Okay. Again, what we have done, we have repeated the same process, but over here we are taking 64 filters and 5 stride, passing it through a ReLU activation function, and after that we have a pooling layer, max pool layer. Then we have repeated the same process for 128 filters. After that we have repeated for 64 filters, then for 32 filters, and after that we are using a fully connected layer with 1024 neurons. And finally we are using the dropout layer with key probability of 0.8 to finish our models. This is where our model is actually finished. And then what we are doing is we are using the Adam optimizer to optimize our model. So basically whatever the loss that we have, we are trying to reduce it. And this is basically for your TensorBoard. So we are creating some log files, and then with that log file, TensorBoard will create a pretty fancy graphs for us that helps us to visualize the entire model. And then what we are doing is we are trying to fit the model. And we have defined epochs as 10. That is the number of iterations that will happen will be 10. And yeah, so this is pretty much it. Model name we have given, Then input is x underscore test to check the accuracy. Similarly, the target will be y underscore test. The labels associated with that test data will be a y underscore test, and which we have encoded basically. So this is how we are going to actually calculate the accuracy, and we'll try to reduce the loss as much as possible in 10 epochs. So till now our model is complete. We are done with it. Next, what I'm doing is I'm feeding in some random input from the test data, and I'm validating whether my model is predicting it correct or not. All right. So I've already trained the model because it takes a lot of time, and yeah, I cannot do it here. So I've already trained the model, and you can see that the loss that came after the 10th epoch is 0.2973, and the accuracy is somewhere around 88%, which is pretty good, guys. And yeah, and I've done the prediction on the test data as well. So let me just show it to you that. So this is the prediction that it has done on few of the images in the test data. So yeah, it is a cat predicted as cat, cat predicted as cat, 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 and dogs as well. There are certain dogs as well. So this is it for today's session, guys. And if you want the code and the data set, go ahead and comment your email ID and we'll mail it to you as soon as possible. So let me just give you a quick recap of things that we have discussed till now. So this is what we have discussed in today's session. We started by understanding how a computer reads an image. Then we saw why can't we use fully connected network for image recognition. Then we saw why we need convolutional neural networks and what is convolutional neural network. After that, we understood how a convolutional neural network works. We discussed all the layers that are involved in it, like convolution, ReLU, pooling, fully connected layer, all those layers we have discussed in detail. And then finally, we implemented a use case which can classify the images of dogs and cats. Alright, so this is it for today's session, guys. If you have any questions, any doubts, just go ahead and type it in the comment section below. You'll get the answer as soon as possible. Thank you and have a great day.
I hope you enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply to them at the earliest. Do look out for more videos in our playlist and subscribe to our Edureka channel to learn more. Happy learning!